So, but this is going to be a case of uniform circular motion. So again, example 6.5, we have the mass M, radius 2.7 kilometers. It's going around this clockwise fashion here, velocity 225. So the question asks us to determine the force exerted by the seat. Yeah, so we have the force at the top and the bottom, because we're going to have force bottom here, and then a force at the top. So we're going to see today if it in fact is the same. This is a nice example of seeing that, and we'll see that it's not the same, we'll prove it. This is a nice example of seeing that you feel heavier at the bottom of loops like this and lighter at the top, almost weightless, depending on how far away you are from the source of gravity, you know, in real weightless type problems. So anyway, we start off, we're going to find the force. We're going to start off with drawing up the free body diagram, as you can see in the example. At the bottom here, we have a normal force from the bottom of the track and its weight, and that's going to be equal to the net force. And we know the net force is the centripetal force that points towards the center of the circle, mv squared over r. So the normal force at the bottom minus the weight equals mv squared over r, and therefore we continue the problem from yesterday. So then we just solve for the normal force at the bottom, which is going to be mv squared over r plus mg. Now, they want you to express the answer in terms of mg. So what we can do is, as you can see there, factor out the mg. And when you do that, this becomes v squared over r times g. Why is that? Because once you multiply this, it's just going to be v squared over r, which is what you have in the original case. So when you factor this out, it's going to be multiplied by g at the bottom, plus 1. And then put in your numbers there to get what the normal force is going to be at the bottom in terms of mg. So we have 225 squared over 270 times 10 to the third meters. Multiplying that by 9.8 and then plus 1. When you do all that, you're going to get 2.91 mg at the bottom. So the normal force at the bottom is going to be twice your weight. So you feel heavier than what you actually are. And for this loop, by 2 times. So that kind of gives you, if we were going to Magic Mountain and you got on the Goliath ride, you can get an appreciation of why you feel so heavy at the bottom of the loop. Okay. So there's that. And then at the top of the loop, we have a scenario of normal force from the top, and then also mg, and put it like that, but mg, so attach it, I guess. And then that's going to be equal to the centripetal force. Now the convention is try to have the net force equal to a positive, because it's a magnitude that we're trying to set it equal to, and generally that magnitude being positive. So therefore all the forces in the same direction as that centripetal force or acceleration will be positive forces, even though these vectors are pointing downward. It goes all the way back to chapter 5 when we were taking a look at tensions or weights. that were pointing down, but if they're going in the same direction as the acceleration, those are going to be positive forces. Same thing goes here. So what we in turn have is forces in the y direction will be mv squared over r. Solve for the normal force from the top. And I think you can see where this is headed. So then once you do this, this comes out to be roughly 0.91 mg. So it's 90% of your weight. So you feel that much lighter than what you actually are. So again, proof of maybe intuition that you're actually going to feel lighter at the top of loops. And this is an extension to weightlessness. So like we're going to see in chapter 13, that as we go further and further away from a major source of gravity or force, like we go away from the earth, if we're going out into space, we're going to start feeling more and more weightless because now we're increasing our distance away from the gravitational force. And that plays right into Newton's law of universal gravitation that states that for any two masses that has a distance r in between them, there's a force of gravity that they both exert on each other, equal and opposite. So that's the idea of that. And we can see that here is that at the top of the loop, you feel actually lighter. Okay, so moving on to 6.2, going into non-uniform circular motion. Okay. So anytime when there is a tangential acceleration along with a radial or centripetal acceleration, the particle in question experiences non-uniform circular motion, CM for short. So if you have a tangential acceleration, it's not the typical uniform circular motion because the speed is not constant around the circle anymore. It's increasing because there's a force on the outside that causes an acceleration tangentially. And obviously there's a force as well. It sets up that acceleration. So the picture we have a tangential acceleration as well as radial. And then we talked about that in section 4.5, where we had this total acceleration action happening. So I'll call it A sub T, A sub R. And if we want to find the magnitude of this, we use the Pythagorean theorem, just as we do with any vector. arbitrary vector ABC, R, A plus B, going back to chapter 3, using the basis vectors there. And so that's what we have. And right, so A sub T plus A sub R. Hopefully that's good with you guys on that conceptually. Ask all questions, of course. Thus, the net force, so call it sigma F or F net, is going to be made up of all of the forces that make up the tangential force. If there were multiple forces, we add those and get this, plus all of the forces that make up the radial or centripetal force. There could be multiple forces there, as we know. From sigma F, meaning sigma F or F net equals MA. So same logic, perspective changes. We're just going around a circle and adding all the forces that make up this total net force here. So we have forces that make up, or that produce these accelerations. So we have, again, in like manner, we have the tangential forces, all the radial forces. To make up the total net force. So this is just a vectorial picture of non-uniform circular motion. Any questions? Anybody need to see something? Always speak up on that because I might be thinking I'm going slow enough. Could be going too fast. Okay, so quick example of this non-uniform circular motion goes to example 6.6. So we're going to determine the tension in this cord and this string, this ball attached to this string whirling around a circle. So we got this going on. So ball at the top. And it's very similar to the fighter pilot question where we had a force at the top, T-top, or in that case, it was a normal force from the top plus his weight. And then we have the velocity at the top. Then, of course, at the bottom here. So we're going to see if, again, you can infer, especially based on the last question, that those forces at the top and bottom will not be the same. We've already shown that the forces at the bottom are going to be larger than the force at the top. It really is the same problem. And they have another picture of this mass located here, and we have a tension at an angle. It's the weight. And of course, This is the components of the weight here. So generally speaking, with these type of questions where it asks you for the force, you want to draw your free body diagrams, put them in your X and Y directions. But even more specific than that, for these non-uniform circular motion problems, you're trying to find the force in the tension in the string, the force of tension here. It's best for you to get all of the forces that make up the tangential force and all of the forces are making up the radial force. So you can squeeze it in there because that's essentially how you do these type of questions. So then from there you can derive the tension in the string. And again, overarching reason, we have a tangential force that is due to this component. This is the force that is driving the pendulum tangentially, and then there's a centripetal force as well. That is due to these two forces at the top pointing inward, and then there's a net centripetal force that's due to the tension pointing to the center of the circle and its weight. So let's just diagram all that out. So the tangential force is the only one here is mg sine. And that is going to be equal to the net force, or mass times acceleration, tangential acceleration. And so the tangential acceleration is just g sine theta. And then the radial force, or centripetal force, is going to be T minus mg cosine theta equals mv squared over r. And this perspective here, this particular perspective, these particular equations deal with this picture here. And these parts of the picture are just going to be examples of what we're going to solve here. Once we get the tension, we can then make an extension for what's happening at the top and at the bottom. Sorry, I wrote top twice. So like I said, it's really like an example of the last question. So let's get the tension, then we can make the substitutions for what's happening at top and bottom. So the overall tension, mv squared over r plus mg cosine theta. And if we factor out the mg, just like we did in the previous question, we'll have d squared over rg plus cosine theta. So that's what the uniform tension is. And then we know that the tension at the top and bottom are going to change based on what we saw last question. So we can use this same equation here to get the expressions for the tension at the top and the bottom. So this is going to be mg times the velocity at the top squared over rg oops, it's already factored. Cosine theta. Well, or we can, for the sake of argument, we can leave it. So they did a +1, but if we can leave this in here if they're taking the angle out and just making it +1, but it's really the same difference. So anyway, the tension at the top will just be the only difference. The only thing that changes that we're looking at the velocity at the top, which is going to be different than the velocity at the bottom. And so we're just saying T top equals mg v top squared over rg plus cosine theta. So the only addition is just the designation of top and bottom. Sorry, is there a question? And the tension at the bottom is just going to be so. Oh. So yeah. Whoops, got that backwards. Sorry about that. So this should be minus, and this should be plus. So it's really, it's same thing as example 6.5. Any questions on that formalism? So the tension at the top will be less than the tension at the bottom, basically. Okay, so there's a couple of questions that deal with that logic for your homework. So just giving you just the basics on how to set this up. So again, finding the tension, you just find out all the forces that are in the tangential direction, as well as the radial direction, solve for tension. So, obviously the tangential direction wasn't really relevant because it didn't have a tension term, but, it's just something to do anyway, just in case there, in other problems, there could be a tension term, but the tension term appears in the radial expression, solve for T, and then just make your substitutions for top and bottom based on example 6.5. You feel heavier at the bottom and lighter at the top. Okay. So at this time, I want to shift up to go all the way to chapter 13. We're going to start sections 1 and 2. Slow down a little bit, give you a couple of questions to answer, and that will do it. So hopefully we have some fun here. Universal gravitation. So this is it's a universal law of gravity. So for any two masses, not just you on the Earth, you on Jupiter, any two erasers, two black holes. It's relativistic idea. two erasers, two planets, Earth, Moon, any two masses apparently obey this law of universal gravitation. Okay. So yeah. So in section 13.1, Newton's law of gravitation, gravity, thing. So I'm just going to summarize all of this. And again, on page 363 is pretty much the same thing, just summarizing it in terms of speaking about it as clearly as possible. Okay. Sorry about that, Stan. I thought that somebody was saying something in the chat, but I didn't see the window. So for any two masses, there's a force of attraction. Oops. That is directly proportional to the product of the masses and inversely proportional to the distance between them squared, so 1 over r squared. So anyway, here's the picture. Mass 1, mass 2, who cares what the masses are? There is a distance from their center of mass, not at the surfaces, from the center of mass, which we will get into in section 9.5 in more detail what that is. But for right now, we're talking about in the interior. So you're talking about, so this is the, moon, Earth. This distance r is at the center. So it's a radial distance. So it's not surface, it's not r, as we commonly understand it. So this is the r in question. This is, mass 1, mass 2. So there's a force of attraction. So this would be the force of 2 on 1, and this arrow would be the force of 1 on 2. Force of 1 on 2 is the same as 2 on 1, just opposite directions. Newton's third law, all that obviously remains consistent. So this is the picture of that. So the equation form, where we can predict certain things, the force of attraction, the universal gravitational force between any two masses is going to be equal to G m1 times m2 over r squared. So it's inversely proportional to the distance squared and directly proportional to the masses, to the product of the masses. So the further away, if we're just keeping m1 and m2 constant, the further away these two masses are, the less force either one of them is going to feel, and the greater the force of attraction. And you get appreciation as we go into the singularity of a black hole, it's, the force of attraction gets higher and higher until we get to an infinite level, because r goes to 0 and f goes to the maximum of maximums, infinity. But that's the basic idea. So that's, And the big G here is the universal gravitation constant, which is equal to 6.73. To write the units every time, but just you're going to become very familiar with this number, universal gravitation constant. One second. Can't seem to get that window. You can. There's a way to get the, especially for any mass on the Earth, you can get the acceleration of gravity. You can get the acceleration of gravity for any planet, actually, from using this equation, yes. Anyway. So that's pretty simple enough. Maybe next time, but I was hoping to get a demonstration. It was, as a student, I had a bunch of regular physics students actually perform the Cavendish experiment, where Henry Cavendish actually calculated the gravitation constant, because Newton knew there was something there, but he didn't actually get the number. It's like maybe 100 or so years later, Henry Cavendish actually performed an experiment to verify or calculate this universal law of gravity and with the constant. And many students did it and got really good numbers. I mean, most of them got on the order of 10 to the minus 11, maybe, not 6, maybe 3, 5, but there's one example in particular from 2018, I think it was, where students did a really good job in getting this number or close to it. So I'll show that for next time. So the big G, pretty much attributed to, first calculated by Henry Cavendish, so-called Cavendish experiment. Had two masses attracted to two larger masses. They were rotating, they were being attracted to these larger masses. And based on the angle of rotation and some other variables in that equation, calculate the big G that we use in this equation for Newton's law of gravity. So 1798, he calculates that some 111 years after Newton published his Principia, his basic pamphlet on laws of physics and other things. So that was 1687. Right. So anyway, as we were talking, so let's say we have mass 1, mass 2, and separated by a distance r going to the centers. So this guy would be denoted as the force of mass 2 on mass 1. This is what this means. So the gravitation force of 2 on 1, positive, goes to the right, and this would be negative 1 on 2. And we know that they're equal but opposite. And so the G m1 m2 over r squared is the same magnitude for both of these, where this Earth and Moon. This is r, of course, constant, but just pointing opposite directions. Now, I was saying yesterday, looking at the perspective of the Earth on the Moon, we're going to see the Moon rotating. If we're on the Moon, we'll see the Earth rotating. From the center of mass of the system, we'll see both simultaneous. But in all cases, Newton's laws prevail. Okay, so So if we were just looking at this empirically, F1 on 2 just be negative G M1 2 over R squared. And then I can do the, so it's this, because we know magnitude is, it's not negative, it's going to be opposite. This is direction, and we know that already. Magnitude and direction is pointing left. Or same thing. Oops. Come on now. Or we can say G M1 M2. This is just another way of saying what's going on up top. So this is saying, this is the magnitude and it's pointing in this direction, or we can just say the conventional, maybe easier way, it's negative, or GM1 M2 R squared to the left. Same thing. Use a unit vector notation or the so-called vector notation, or standard vector notation. And thus, likewise, F2 on 1 is positive. And this would be staying the same. So there's an understood positive. It's going to the right, or we can write it in the standard or the unit vector notation, where R21 means to the right towards mass 2. That's the basic equation there. So Sin asks a very good question. Can we calculate 9.8 from it? Well, I'm going to give you that as an example for you right now. You can absolutely do anything with this. This is universal. So we can go to Mars, Venus, asteroid, and calculate what the gravitational field is going to be at those points. How do we do that? 13.2. Free fall acceleration. We know what that is. Anywhere, not just here, wherever you may be. Free fall acceleration and gravitational force. So the relationship. So what do we have? So we're on the Earth for right now. SpaceX get launched out there somewhere. A particle of mass m falling towards Earth. Feels or has, pejorative, so experiences a force. We can say mg, but it's universal, so we might as well use the universal stuff because we can apply this anywhere. So with M1, M2, or ME is going to be mass of the Earth, and this is U, or rock, or whatever is falling towards the Earth. And this is basically, so Earth is here, and this mass is falling down towards it. It's separated by And we're gonna approximate this as to be local to the surface of the Earth. You know, this, just because it's above the surface in this picture, it's not in space. It's just localized. Because this equation changes, if we're in space, it's going to be r plus h, the height above the surface, r plus h squared. Because this r really is obviously this. So don't be confused by that. It's following locally. We know intrinsically by first principles, Fg is equal to mg. Those masses go away because it's talking about the mass. We're looking at the perspective of Earth pulling on this mass, and we want to get the gravitational field of the Earth with respect to that mass. And obviously it's going to be the same the opposite way, because the field is non-respective of mass. So G equal to GME over R squared. So you can get the gravitational field on the Earth by knowing the mass of the Earth. You can get the gravitational field on Saturn by knowing the mass of Saturn, you know, or whatever, you know, case may be. So why don't you take a couple of moments right now? I've been talking at you a lot so far. And let's verify from this equation that we can get 9.8. You know, show that it's 9.8, and then what is the gravitational field on Saturn? And how do we get the masses of both? There's a table on page 370. There's a table of masses of all the planets, the radii. So go there and solve these two problems. Just to verify that you can get 9.8 from here and whatever the mass or the gravity on Saturn is. I like this, useful planetary data. And we'll just stay here. You don't need to break anywhere. No, it's not going to be, it's just going to be the radius of that particular planet. So we're not orienting anywhere because that's arbitrary. So this is radius of Earth. Why did that go away like that? Radius of Earth and radius of Saturn. This shouldn't take too long. Just a healthier perspective here. On the surface. Be bigger. Okay, so basically, go to any planetary body, and you can use the universal law of gravity to get the gravitational fields anywhere. So if you all get that, or still working on it. So just send me a private message if you got it, or you need help, or specifically in chapter 13, like what, specify your question. But everything before that, you're okay? This is you question on the exercise. Okay, what we're doing here is we're calculating. We want to verify that using this expression, we can get Earth's gravity of 9.8 meters per second squared. And then we want to use the same relationship to get the gravity on Saturn. And so, be more specific. And what we did here is we had a mass falling towards Earth. We know that the local force of gravity is going to be m times g. And so that, I'm going to set that equal to the universal gravity equation, and the m's cancel out. And we're trying to solve for g on Earth, and then likewise the gravity on Saturn. And in order to get the mass of Earth and Saturn, you can go to page 370 to get that data. Did that clear that up? You know what to do now. Yeah. As you're doing that, we're going to see that, like I said, this is going to be an example of circular motion. Moon orbiting the Earth. Okay, we're going to connect that back to conservation of energy. Using conservation of energy principles, we can calculate exactly the speed or the escape speed necessary to leave the gravity of the Earth, which of course, everyone at NASA, SpaceX, anywhere, they know that so much more. Just from using energy principles, we can launch things into space. we have to calculate the speed first, and then we have to make a rocket with enough fuel mass in order to achieve that velocity, speed, one direction, but and it's same planet. But yeah, so again, it's very important, the basics of circular motion. We can expand that to orbital motion, which is really the same thing. And then we can use energy principles to figure out escape velocities, escape speeds, and play around with other physics to figure out what speed do we need to be in order to go to a particular orbit, low Earth, mid Earth, whatever level that we're trying to go. Yes, that's a very complicated answer, but yes, it's a combination of spectroscopy, which is I mean, actually I had a project like that in undergrad astronomy class. It's pretty involved. Now they do it so much simpler, but you can look at spectroscopic data. You can look at the period of rotation. Basically, use Kepler's laws to get the mass of other planets. A small answer to that, but combination of Kepler's laws, spectroscopy, that's pretty much the simple version of how you can do that. But yes, there's a simple answer for a complicated process. And we'll be talking a little bit about Kepler's laws next time. So you verify that Earth's gravity is 9.8 from this. Let's go ahead and do that, shall we? So put the big guy in here. So mass of the Earth, remember it's still 5.98, 10 to the 24th. It's 6.37 times 10 to the 6th squared. So all you do is do that, you should get 9.8. And then likewise with the gravity of Saturn, .68 times 10 to the 26 radius. So that's the long and short of that. Calculate both of those. So for G, 3.99, 14. .06. Let's see what we got. No, Okay, sig figs, yada, yada, get 9.82, well, roughly 9.8. Right, meters per second squared. So verify that now. We use this, use the same logic to get gravity on Saturn. Yes. Due to what? I haven't heard of that. I don't know what it would be growing as a result. It's not going to arbitrary. Remember, things just don't happen abiogenetically, right? So if you're positing that the Earth's mass is growing, it's going to collisions. We're not getting bombarded like that from many asteroids, as allegedly it was. I don't know any other source that would cause it to grow in mass or in size. I haven't heard of that, but it's always new stuff. I'm not sure. I have to verify that. Yeah. You know, it's the beauty of science, beauty of physics, that don't know everything. And try to figure it, somebody makes a claim like, let me go check that out. So this 3 point, with all the sig figs, is going to get more precision or accuracy, and that too. So I'm going to say 3.79 10 to the 16th, 5.85. That's 3.42. I see the exponents larger. $11 meters per second squared. Expecting something more dramatic than that, but definitely going to be more. Supposing calculations, we do that again, but allegedly on Saturn, 11 meters per second squared, Earth 9.8. So that's, you can use this relationship to get gravity on any surface, any planet, asteroid, comet, wherever. So the last bit I want to do for section 13.2 is to now, we're going to be on the Earth, and now we're going to go into space, and we're going to see what is the force of gravity going to be at some point from the surface of the Earth. We know already from example 6.5, 6.6, that you're going to feel weightless, that the force that you're going to experience is going to get less and less. We also know that from Newton's law of universal gravitation here, that as R increases, your force drops. It's just a mathematical inverse relationship. R gets large, F goes down. So you already know intuitively that it's going to be smaller. So let's just see what that equation looks like. And therefore, yeah, just like the force is going to get smaller, the gravity is going to get smaller. So you're going to feel lighter. So consider mass above the Earth, height at height h above. So now we're not just looking locally as we did in the previous example. So we're going to look at something like this. we're going to be some distance h above. So it's going to be RE plus h as your radial distance, right? You already see where this is going. That's going to not only linear, but quadratically going to drop. We're going to get larger rather, and then your force is going to drop. The further away you get from this source. You know, as R goes to infinity, F goes to 0. So the R in the equation, universal gravity of RE plus H, and then, so we have just an arbitrary mass M, and then mass of the Earth. Right? And so, and likewise for the gravity equation, it's the same relationship. Wherever, you know, force does, gravity does proportionately, right? So, and directionally. G M E over R squared, or becomes proof, mathematical, that you're going to feel lighter. It's have the same mass, but you just feel lighter. And then weightlessness is apparent. You know, obviously you do have weight because you still got mass. It's just that now your forces are balanced. The force from the Earth and the force by the rocket thrusters, right, are the same, but even better than that, because as the spacecraft is in orbit, there is no force tangentially, right? So you're going to be going at a constant speed, weightlessness. So again, the basic principles, centripetal motion or circular motion, hopefully you can start to apply them and see why you're so-called weightless, because tangentially there is no force, just radially. That's why you're kept in orbit. Otherwise, cut off the source of that force, which you can't, but let's say you do, you're floating out into space. And whatever the direction you were pointing at the time the force was cut. So that's it, really. Any questions? Time for questions. I'm done. To talk about the